So please understand that the data link layer is represented by layer 2 of the OSI model, and the book will reference the internet model. It's responsible for moving messages from one device to another. It controls the way messages are sent on media. It organizes the physical layer bit streams into coherent messages for the network layer. And the major functions are media access control, error control, and message delineation. In other words, splitting up the messages. So keep in mind the layer 2 is represented by the switching and the movement of data. Thank you. Now we'll discuss media access control. This controls which device transmits and when it transmits. It's important on multi-point or shared circuits, so a lot of wireless involved there, and half-duplex point-to-point circuits. We'll be discussing two approaches of media access control, the contention access and the controlled access. And we'll display a graph showing where the happy spot is. Thank you. I'm going to read the slide here first about contention. Contention transmit whenever the circuit is available with no centralized control. They're common in Ethernet LANs. When devices transmit at the same time, a collision will occur. So devices are asked to be polite, and I put that in quotes, and follow these steps. So they listen for other traffic, so they're looking for other traffic, and if another device is transmitting and there could be a collision, it will wait. Otherwise, it's going to transmit and keep listening. And if another device starts to transmit, the polite device will stop and wait. So I look at contention as driving in a country where they don't have a lot of traffic lights and a lot of traffic laws. You've all seen clips on the internet and on TV of traffic intersections with no stoplights where there are very few traffic laws. And traffic does seem to flow through, and people do seem to get around, but it's a lot more chaotic because there is no centralized control. In the case of traffic, it would be the stoplight. So hopefully that gives you a better idea of how contention works. Now let's look at controlled access as the exact opposite. On this slide, we say that controlled access is very common in a wireless LAN because it's an access point where there's a multi-point connection, so it would need to be controlled, and usually the access points handle that control. Access is done by requests, so each device must get permission to transmit, and it's similar to raising a hand. And that raising of the hand is called polling, and there's roll call polling and hub polling. With roll call polling, a central device or controller determines which devices can transmit. Each client is checked periodically to see if it needs to transmit. On the other hand, hub polling is when one device begins the poll and then passes it to another device until everything is reached with all of them. So you probably heard of token ring networks. That is a hub polling type of controlled access. Now, I would say that controlled access is like driving when you do have the stoplight and everything is under control. So which way is better? Well, we'll find out in a second. In a previous slide, I discussed the happy point, which is where controlled access and contention access intersect. With low traffic, the higher overhead of controlled access makes contention more efficient. But with high traffic, controlled access is better. So the crossover point used to be 20 devices. I think that's going to continually become more and more as time goes on and networks become faster and faster. But this is all based on relative response times and traffic. So please understand the diagram, and thank you. Now we're going to discuss error control. So there's several different types of network errors. There's network errors involving corrupted data and completely lost data. These problems are usually caused by errors in transmission and not through humans. The network should be designed with error prevention, error detection, and error correction in place. This will always help you, and almost every network encounters certain types of packet loss, and most systems have error control built into them nowadays. Thank you. Now we'll discuss some sources of network errors. Line noise and distortion involves electrical media most likely, and they're undesirable electrical signals, and they can degrade the performance of a circuit. There's all sorts of sources for this noise, this types of noise and distortion. I don't know if you've ever heard, but when you put a Ethernet wire near a fluorescent light, that can create a lot of noise and electromagnetic energy that is not helpful for the circuit. The manifestation can include extra bits, flipped bits, or missing bits. So that can confuse the data, and when you go through the error checking algorithms, this is often detected. Thank you. Here are some examples in the spreadsheet below. It tells you about the source of the error prevention. It gives you the cause, and it gives you what you can do to fix it. So look this over. This will give you an idea of what causes the errors. Thank you. All right, now let's talk about the concept of error detection. So receivers, in other words, the receiving machine, needs to know when the data transmitted is not correct. So there's several ways of adding what we call a check value to the message. And that check value is an error detection value. And it is produced by a mathematical formula which can be very simple or very complex. And we'll go into that. When calculating the check value, both the sender and the receiver calculate the check value. In other words, they work together to determine what the check value will be. Sender tests whether the check values match. Thank you. This is an interesting concept. It's the parity check with error detection. It's accurate about 50% of the time when you're trying to determine whether a bit has even or odd parity. Previously, I've mentioned the ASCII table and its importance. And ASCII characters are represented by binary representations. So below you see the example of the letter A in its binary representation on the ASCII chart, and the letter C in its binary representation. If you'll count the number of ones in the binary character for the letter A, it equals 2, which is even. So the parity bit is 0, and that's a representation of even parity. C is the exact opposite because the binary count is 3, which is odd. So that's how that works. It's simple, but it only detects errors 50% of the time, and it's almost a 50-50 check. So it's helpful, but it's not perfect. The parity check is very common with serial communication based on RS-232 protocols, and we'll go into that a little bit more later on. Thank you. And just to carry that a little further, let's say we receive the capital B. The capital B is also an even parity number. In other words, there is only 2 number ones in the binary representation of the capital B. So it would also throw the parity bit of 0, when the actual character it was expecting would have been A. So the parity bit would actually say that was correct because the parity bit is going to be 0 whether it receives an A or a B. Hopefully that makes sense. The checksum involves the use of check values. So this is a much more efficient form of error detection, and it will detect up to 95% of errors, and it's typically a 1 byte value. Thank you. So if there is an error detected, it must be corrected. You can't send faulty data back and forth. There's several error correction techniques. There's retransmission, or there's forward error correction. Those are the two big types of error correction. With forward error correction, the device receiving the message can sometimes have the ability to correct the message without the need to retransmit. However, if retransmission is necessary, it's usually the most simple and most common way of correcting errors. So retransmission, or backward error correction as it's also called, involves ARQ requests, which ARQ stands for Automatic Repeat Request. I know, why isn't it ARR? That can be a stop and wait ARQ, or it can be continuous. And retransmission can also provide flow control by limiting the number of messages sent, and this can be useful if we start seeing a lot of errors. Thank you. So, you all may think that you see a lot of errors on wired connections. Right now, as I read my email, I know the IT department at Albertus would agree with that. But actually, on wired connections compared with wireless or radiated connections, errors are pretty rare. Most data link layer software today does not correct errors. It only detects them, and it says, hey, these frames have errors, and it discards them and they're resent. Error correction must be done at a higher level. So error correction is done at the transport level in practice. And as you know, the transport level sits above the data link layer on both the OSI model and the internet model. So keep that in mind. We'll go into some error correction details when we do discuss the transport layer or the TCP UDP layer. Thank you. Now we'll discuss protocols on the data link layer. The classifications are asynchronous or synchronous, and we'll be discussing those. The protocols differ by the message delineation, frame length, and frame field structure, which we'll also discuss. Thank you. First, we'll discuss asynchronous serial transmission. It's an old protocol used in teletype, and it transmits one character at a time. So like I said, this is basically the RS-232 protocol, and it's delineated by start and stop bits. So if you remember, any of you setting up modems and stuff like that, there's the transmission type, which might have been 8 none and 1, or 7 none and 1. So that's the 7 or 8 would represent the number of message bits. None or 1 would represent the parity bit, and then the other number would represent the start and the stop bit. So you probably remember that, but that is the basics of serial communication and serial transmission. Thank you. Now we'll discuss synchronous transmission. Characteristics include the data sent in a large block called a frame. It includes addressing information, and it includes synchronization characters to let the receiver know when the transmission begins. Protocol examples include SDLC, HDLC, Ethernet, and point-to-point protocol. Thank you. There's different types of data link protocols, as we saw and discussed in the previous slide. The synchronous data link control protocol, or the SDLC protocol, is a synchronous bit-oriented protocol, and it was developed by IBM. It uses bit stuffing to overcome a transparency problem. So what that means, and I'm not going to hold you to it, it means it does a bunch of zero insertions, so you get a lot of zero padding with that. It's most likely a de facto standard. Now the Ethernet operates under a de jure standard because it's an IEEE standard, and we're going to go into that organization a little bit later, so I won't discuss it now. But The Ethernet standard is a de jure standard, and we discussed that, and I said I was going to use those words throughout the class. And there's also Ethernet 2, which is an up-and-coming standard. Ethernet, as you probably have all heard of, is the most commonly used LAN protocol. Like I said in previous slides in the classroom here for the on-ground students, Ethernet is the protocol being used for the LAN. And it uses contention, media access control. So we discussed contention and what that is. And if you need to go back and look, please review the slide. But that's good information. Thank you. We've discussed some LAN protocols. Now we'll discuss what's probably the most common WAN or wide area network protocol, and that is the point-to-point protocol. There's a couple of bullet points we want to discuss involving through point, and that's basically that it's more complicated than simple protocol efficiency because it depends on retransmissions and delays, and it is measured in TRIB, or the transmission rate of information bits. Thank you.